In this section, we go over some spaces of Rn and Rm called the row space, the column space, and the null space that come from an m by n matrix. These subspaces will play a role in understanding systems of linear equations and linear transformations. If A is an m by n matrix, the row space is just the subspace of Rn spanned by the row vectors of A, and the column space is just the subspace of Rm spanned by the column vectors. Right, so the individual rows are vectors in Rn, right, because n is the number of columns. And m is the number of rows. Right, so a row, an individual row, is n dimensional, right, because the number of columns are the individual coordinates in the row vectors. And then likewise, the number of rows gives the number of coordinates in the individual column vectors. And so the column vectors belong to Rm. Okay, so first we discuss the row space and how we obtain a basis for the row space. Right, so I mean, basically, all of these subspaces are going to be determined by looking at the row reduced echelon form of the matrix. So the reason we can look at the row reduced echelon form is because the statement here where if A is row equivalent to row B through row operations, then they have the same row space. Right, so even though the individual rows of B are different than the rows of A, basically by doing row operations, it means that the rows of B are linear combinations of the rows of A and vice versa. And because they're just linear combinations of each other, when you look at the span, it generates the same subspace. And so from this, we can obtain a basis for the row space by taking the non-zero rows of the row reduced echelon form of the matrix A. So here we take a look at an example where we try to determine a basis for the row space. Right, so this is our matrix A. Right, so we're going to look at the row reduced echelon form. Right, so we can see that this is our matrix A here. So we calculate the row reduced echelon form. This is what we get. And so now we can obtain the basis. Right, so here, if you look at the row reduced echelon form, there's three non-zero rows. So let's call them W1, W2, W3. Right, so these three rows will form the basis for the row space. So the first row is 1, 0, 1, 0, 1. The second row is 0, 1, -2, 0, 3. Then the third row is 0, 0, 0, 1, -5. And so this is our basis. So in this example, the row space is only 3-dimensional, whereas there are actually 4 rows. The reason is because one of the rows is a linear combination of the other rows, right? And so the process of doing of Gaussian elimination, putting it into row reduced echelon form, gets rid of the dependencies among the rows and only leaves the linearly independent rows. Right? So they're linearly independent because of this staircase pattern among the leading entries. And then again, it spans the entire row space because of the discussion here. And so it forms a basis. Okay, so now let's turn our attention to what's called the column space, right? So that's the subspace of Rm generated by the column vectors of a matrix. Okay, so to determine a basis for the column space, we can again look at the row reduced echelon form of the matrix. However, because row operations don't form linear combinations of the column vectors, we have to view things slightly differently when looking at the column space. So there's going to be 2 methods to try to find a basis for the column space. So the first is to look at the row space of A transpose. We can do this because the columns of A are exactly the same as the rows of A transpose, right? So that means that the row space of A transpose is exactly the same thing as the column space of A. So we can do it that way. Or the alternative is, instead of looking at A transpose, you can still look at the row reduced echelon form of A, but instead of taking the columns from the row reduced echelon form, what we do is we take the original column vectors from A that correspond to where the leading ones or pivots occur in the row reduced echelon form. So in this example, we'll see how to obtain that basis using both methods. We'll see in the course of using each method that the basis that we get from each one is going to be different, but in the end it doesn't matter because they still form a basis for the same subspace. Okay, so let's look at method 1. Which is to look at the row reduced echelon form of A transpose. So this is the same matrix from the previous example, right? So I can just use the same matrix from before. So I'm trying to calculate the row reduced echelon form of A. Oops, not A inverse, I want A transpose. So I do the transpose, except you'll see there's going to be a problem. Right, so here it says invalid dimension because A is 4 by 5, so that means A transpose is 5 by 4, and the calculator doesn't like it when you try to do the row reduced echelon form for a matrix that's long in this shape. So so what you can do is extend it. Right, so okay, so let me, what am I doing? So I want to do A transpose. So let me copy this into a new matrix. So A transpose, let me transfer that into matrix B. Right, so now we see that B is 5 by 4. And I'm just going to extend an extra column of all zeros to turn it into a 5 by 5 matrix. And so now I have an extra column for all zeros. It's no longer, now it's square, so I can do the row reduced echelon form. And so now I just need to calculate the row reduced echelon form and ignore the last column of all zeros. Okay, so this is what we get. Right, so again, ignore this last column. Okay, so the rows of this form now my basis vectors. Right, so S1 is 1, 0, 2, 0, and then second row is 0, 1, 7, 0, and the third row is 0, 0, 0, 1. So I write them as column vectors because this is for the column space, right? So this is row 1, this was row 2, this is row 3. Okay, so I get this as the basis for the column space. So the dimension of the column space is also 3 in this particular example, and we'll eventually see that the dimension of the row space and the dimension of the column space always have to be the same, even though they're subspaces of different vector spaces. Okay, so that's method 1. Now let's look at method 2. So where we look at the row reduced echelon form of A. So that we've already calculated it previously. So row reduced echelon form of A is here. Right, so we want to look at where the leading ones occur. Right, so first row, the leading entry is in the first column. Second row, leading entry is in the second column. And third row, leading entry is in the fourth column. Right, so I want to pay attention to which columns they occur in. Right, so the leading ones, or sometimes they're called pivots, occur in columns 1, 2. Okay, so one thing you want to be careful about is when you try to locate the leading ones, you go by rows, right? So row 1, row 2, row 3. And then what you want to pay attention to is which columns they belong to. So let me say that the leading ones for rows 1, 2, and 3 belong to columns 1, 2, and 4. Okay, so we take the original column vectors in A that correspond to where they occur in the row reduced echelon form. So I need to take the original columns 1, 2, and 4. So I get now as my basis vectors, so column 1 would be -2, 1, 3, 1. Column 2 would be -5, 3, 11, 7. And column 4 would be 0, 1, 7, 5. Okay, so and you can see that S1 and S2 are different, right? So they're two different bases, but the claim is that they both are bases for the same subspace, the column space. So how can we see that? Well, we can see that the basis vectors for S2 are just linear combinations for the basis vectors from S1, and because they're linear combinations of each other, they generate the same subspace, right? So let's call this V1, V2, V3. Let's call this W1, W2, and W3. Right, so so even though S1 is not the same as S2, they both generate the same column space. By seeing that they're linear combinations of each other. So in terms of, it's easier to look at the W's in terms of the V's, right? So if I look at W1, so I need a -2 in this component, right? So I need -2 here, so that's V1. And then I need a 1 in the second component, so that means I need 1 V2. And and then now I need a 1 in the last component, so that's +1 V3. I mean, you can see that the coordinate here matches up, right? Because -4 + 7 is equal to 3. And then you can do the same thing for the other vectors, right? So W2, right? So I need a -5 here, so I need -5 for V1. And then I need a 3 in this component, so I need a 3 here, that's V2. And then I need a 7 in this component, so that's 7 V3. Again, you can check that the 11 here matches up, right? Because -10 plus 21 is equal to 11. W3, I need a 0 from V1, and then a 1 from V2, and then a 5 for V3. Okay, so again, I mean, they're different bases, but it's okay. I mean, a vector space can have different bases. So both methods will produce a basis for the column space. Okay, so as mentioned previously, this statement here says that the row space and the column space have the same dimension, right? So when you're finding a basis for each subspace, they should have the same number of vectors. However, this is not the same as saying that they're the same, right? So they're not the same. So the row space is typically different from the column space, even though they have the same dimension. And so we can give a terminology to this, to what this dimension is, and it's called the rank. So the rank can be taken to be the dimension of either the row or the column space of the matrix. And basically, because the rank comes from the basis vectors, or from how we determine the basis vectors for the column space, the rank is the same as the number of leading ones, right? So in the process of locating the leading ones, or sometimes they're called pivots, you can just count up the rank, right? So this is the same from the example from before. We see that the rank has to be 3. Okay, so the final subspace we're going to introduce is called the null space. So the null space is just formed by all the vectors that are annihilated by the matrix, right? So it's just basically all the solutions to the homogeneous equation AX equals 0, right? So all the vectors such that when you apply the matrix A, it gets annihilated and becomes 0. So we already know how to solve homogeneous equations, right? So you just look at the row reduced echelon form augmented with a column of zeros on the right, and you can get the solutions from there. So before we look at an example, you should notice that when you're solving this homogeneous equation, the free variables come from the columns of the row reduced echelon form that do not contain the leading ones. And because we know that the leading ones tell you what the rank is, the dimension of the null space, which is called the nullity, so the nullity comes from the free variables, and because the free variables again are the columns that do not have the leading ones, you have this relationship where the nullity is the number of columns in the matrix minus the rank, right? Because in a matrix, the number of leading ones plus the number of free variables has to be the number, same as the number of columns, right? So in this matrix here, right, so the rank is coming from columns 1, 2, and 4. The free variables are coming from columns 3 and 5. And then that together describes all of the columns. Okay, so this is just this relationship written again in this form, right? So the total number of columns is always equal to the rank, which is the number of leading ones, plus the nullity, which is the number of free variables. Okay, so now let's try to determine the null space for the matrix from before. Right, so we've already done the row reduced echelon form. Right, so let's label the variables. Right, so first column is x1, second column is x2, third column is x3, fourth column is x4, fifth column is x5. Right, and right, so the null space is just, again, solving ax equals 0. Right, so we're solving the augmented matrix with the column of zeros on the right. But because the entire column is all zeros, when you do row operations, they still stay all zeros, right? So I can just take the row reduced echelon form of A and just augment all zeros. In general, you can't just augment this vector here unless it's all zeros like this. But in any case, let's continue, right? So, okay, so we need to determine the free variables, right? So you see that the leading ones occur in columns 1, 2, and 4. So the free variables are for columns 3 and 5. So that's x3 and x5. Right, so we can introduce parameters. So I need two parameters. Let's say s and t. And now for x1, x2, and x4, we translate the rows into equations. Right, so row 1 says x1 plus x3. Well, x3 is s. Right, so plus s, and then plus x5, which is t, equals 0. And then row 2, so x2 minus 2 x3, which is s, plus 3 x5, which is t. And then row 3, x4 minus 5 x5, which is t, equals 0. And then I can solve for x1, x2, x4. So this one says x1 is equal to minus s minus t. x2 is equal to 2s minus 3t. And x4 is equal to 5t. Okay, so now let's put it all together, right? So x1, x2, then x3 is here, x4, and then x5. So what do we have? So the null space of A is right, so let's put it together here, right? So x1, x2, x3, 4, x5. x1 was minus s minus t. x2 is 2s minus 3t. x3 is s. x4 is 5t. x5 is t. Okay, so actually, to describe it in a more readable way, let's separate the variables s and t. Right, so we separate the free variables. Right, so s. Right, so the coefficient of s here is minus 1. Coefficient of s here is 2. Coefficient of s here is 1. This doesn't have an s, so that means the coefficient is 0. This doesn't have an s, so the coefficient here is 0. And now t, the coefficient here is -1, coefficient here is -3, doesn't have a t, so coefficient is 0, coefficient here is 5, and the coefficient here is 1. Okay, so the null space of A is this, where s and t are real numbers. And so this immediately gives us a basis for the null space. And the nullity is 2. Okay, so this completely describes the null space. And if you want to make sure all the calculations are correct, you can check that. Check the basis vectors, right? So what does it mean to be in the null space? Well, it should be annihilated by the matrix A, right? So let's take the matrix A. So let's check. Multiply each of the basis vectors -1, 2, 1, 0, 0. So when you do matrix multiplication, it's -1 plus 2 plus 1, right? So what do we have? It's 2 minus 10, which is -8, plus 8, which is 0. Then this would be -1 plus 6 is 5. 5 minus 5 is 0. And this would be -3 plus 22 is -19. Is 19. Minus 19 is 0. And then this would be -1 plus 14 is 13. 13 minus 13 is 0. So there you get this. It should be a 4-dimensional vector, right? Because this is 4 by 5 and this is 5 by 1, so the resulting should be 4 by 1. Okay, so do the same thing for the other one. So -1, -3, 0, 5, 1. And so you can calculate it, right? So where's this? This is 2 plus 15 is 17. And 0, 0, and then -17, so that's 0. Next one would be -1, -9 is -10, plus 5 is 0. It's -3. -33 is -36, plus 35 is -1, -1 plus 1 is 0, and then -1 minus 27 is -22, -22 plus 25 is 3, 3 minus 3 is 0. Okay. So both these vectors are in the null space. Okay, so on this last page, the discussion here is just a reframing of what we know about consistent systems, consistent linear systems, in the context of the discussion on the null space. Right, so basically, if you have a consistent system where there's at least one solution, then every solution can always be written in the form xp plus xh, where xp is a particular solution and xh is a vector in the null space. And in the case where there's exactly one solution, then that means that the null space is just the zero space, and so the only solution is the particular solution in that case. And then the discussion here is just shows why it's set up this way. So here, let's look at this example here that demonstrates this in action, right? So here I have a system of linear equations and I want to find all solutions to it, right? So the way we've always done it is to set up the augmented matrix and then find the row reduced echelon form of this augmented matrix, right? So the first column corresponds to the variable x, the second column corresponds to the variable y, the third column corresponds to the variable z, right? So row 1 has a leading one here, row 2 has a leading one here, right? So column 2 doesn't have any leading one, so that means that y is free, right? So we parameterize y to be t, and then we translate the other rows, right? So row 1 in turn becomes x minus 2y, which is t, equals 4. Row 2 becomes z equals 0, and then row 3 is just 0 equals 0, which is not needed. And so solving for x would be 4 plus 2t, and y is t, and z is 0, right? And so if you separate the variable here, right, so there's this constant and then the variable term, right? So if you separate the variable, then the vector with coefficient t is the homogeneous vector, this vector xh, and then the vector without the t is the particular solution. Right, so you can see that this vector is particular. This vector is the vector coming from the null space. And then finally, this last statement here is just something that we can take from the discussion from this section, right? So basically you can determine that a system of linear equations like this has at least one solution if and only if the vector b is a linear combination of the columns of A, right? So I mean, it's not so easy to see, but in fact, because this has a solution, this is true, right? So this vector here is a linear combination of the other three vectors.